final speaker before lunch.
Germano Heinzelmann.
Germano Heinzelmann, yes, thank you. And he's going to tell us about this attachable release method and how we can apply it to binding affinity. So without further ado,
Thank you.
actually remember to start.
You have the pointer?
Yeah.
Okay, so I'm going to talk about this code that I wrote in Python. It applies the attach pull release method, which is a method for absolute binding free energy calculations to different proteins. But I'm going to start, I applied this initially to Bromodomains, and it can be extended to other proteins. I'm actually a faculty member at the School of Physics in Florianópolis, Brazil, at the Federal University. So first I'm going to talk about, just quickly talk about bromodomains and what are these proteins, then how we apply this attach pull release method to these proteins, and then talk about why do we do this attach pull release. It's because of you can get really high performance simulations using the PMEMD CUDA module from Ember 16. So it has a few limitations, such as for some restraints you have to use single atoms, not center of mass restraints. But we can overcome them and hopefully get good results. So bromodomains, they read these acetylated lysines in the histone tails. They are domains from bigger proteins, and these bigger proteins, they recruit other proteins. So they're related to epigenetic changes. They all share a similar structure. They have it's like four helices, but these different loops here, they're all they share a very similar conformation. This one is the most flexible part, and the part that's mostly different between all bromodomains, which is called the ZA loop. That's because this is one of the Z helix, and also the other is the A helix. They're suitable for these types of calculations because they're not very big, they're small, and they're relatively rigid. So the conformational space is not that large if you can restrain it properly. The ligands are exposed to the solvent. So what we do, the APR is actually an umbrella sampling method. So if they're exposed to the solvent, you don't have clash steric effects when you pull it out to the solvent. And there's also plenty of hundreds of crystal structures with different ligands bound to this bromodomain. So they provide also a great testing ground for this method and see how far we can go doing this. And if we're actually able to not only calculate binding affinities, but also try to perform a little bit better than docking programs. Then again, using the high performance simulations. So this is the setup. This is absolute binding free energy, so you have to be careful with all of your restraints. So in this case, we have to restrain all the 6 degrees of freedom from the ligand. So this distance here, this dihedral here, T1, and this angle here, A1, this you can think of this as the R distance, the polar and azimuthal angle. So it's going to restrain this to a volume element in spherical coordinates. And the other dihedrals and angles, you can see them as Euler angles, so they're going to restrain the orientation of the ligand. So that's important because you want your system to be tight when you pull it out. So like I said, to restrain the conformational space, because if you have too large of a conformational space, you're going to have sampling problems, and then you're going to need a lot of simulations. So these three are dummy atoms, so they don't interact with the rest of the system, but they're needed because they have to keep everything else in place. And like I said, we can only perform, PMEMD now has center of mass distance restraints, but not angles and dihedrals. So if you want your Euler angles and your position restraints to be self-consistent, you have to use single atoms for everything. So these three are the protein anchor atoms, in which we're going to restrain the protein in the same way using 2 angles, 3 dihedrals, and 1 distance. And these are the 3 ligand anchors that we're going to restrain them relative to this dummy atom. So these are not relative restraints, they have more of an absolute restraint character because these dummy atoms, they're restrained in space. So restraining these and these relative to the dummy anchors. So they're positioned in a way that these 2 angles here, A1 and this one, are always 90 degrees. This dihedral is always 180, and this dihedral here is always this dihedral here is always 0, and this dihedral here is always 180. That's just to keep the system well organized. And also the first anchor of the protein, the ligand, and the 3 dummy atoms, they're all in the same plane. So this is all done automatically, some geometrical transformations, and then you get to place everything where it should. So we use this to calculate the standard binding free energy of several ligands to this bromodomain. This is the first bromodomain from the BRD4 protein. And since it's absolute restraint, absolute binding free energy, you have to apply restraints. So you attach, first when in the binding site, you attach conformational restraints to the protein, then conformational restraints to the ligand, then translational and rotational restraints to the ligand. Then you pull it out, then you release the ligand translational and rotational restraints using analytical, solving an integral analytically because the bulk is isotropic. And then you release the ligand conformation, and then you finally release the protein conformation. So the order that it goes in is the reverse order when it leaves. So when you attach this one is attached. When you attach this one, these two are attached. When you pull, they're all attached, and then you release them one by one. These two are released in a separate box. You don't want them to be in the same box because you don't want them to meet each other. So the ligand release, conformational release, and the protein conformational release are done in a separate box. Since we're restraining this relative to these dummy atoms, you have to make sure that we're not calculating the protein translation and rotational restraints. They're just keeping the system in the lab frame. So we have to make sure that that's not interfering with the internal degrees of freedom of the protein. So we did the RMSD analysis, but also we analyzed the phi and psi angles or Ramachandran angles from the residues that have the protein anchor atoms. You can see the distribution is very similar. There's also a RMSD analysis, which is not here, but it's in the paper, and it's also, the agreement is very good. So we can safely say that, at least for this protein, the fact that we're using kind of absolute restraints, they're not interfering with the restraining internal degrees of freedom of the protein. So this is not calculated. So it's just there all the time to keep the whole thing not moving around in the box. We also identified a conformational change once the ligand is out. There are no, as far as I know, there are no NMR structures for BRD41, and the crystal structure, the Apple crystal structure, does not have this. So this might be an artifact from the simulation, this conformational change. It works like as a hinge. So you have two aspartate residues here, and it just, these ones, they change their angles. It kind of flips like that. And you can actually calculate this using only one reaction coordinate, which is actually this dihedral here, the green one. So luckily, it was a conformational change, but it was a well-behaved conformational change. So we were able to calculate this just using single atom restraints as well. So we applied the restrain all the other dihedrals, turn this one, and then release them. So we use a separate APR approach just for this conformational change. It doesn't really interfere with the relative binding free energy because it's an offset free energy because the ligand is not there anymore. So it's just something that happens to the protein once the ligand is not there. So even though it does affect the final binding free energy, it's not going to affect the relative binding free energy between different ligands just because the ligand is out. It's just not there anymore. So we don't have to worry about for relative affinities if you want to just compare ligands. So we tested it for 8 ligands to the first to this bromodomain. A lot of simulation time, but they're highly efficient. So we could use 7.5 microseconds per ligand. Tested 8 different ligands and had some statistics using different water models, different trying GAF and GAF2. The one that performed the best was the SPCE with GAF. You can see the correlation coefficient. And you also have, you actually have 2 sets of results. One relative to this open state, which is the one that after the transition, and one relative to the closed state. There are other studies that they did not identify this, so they calculate everything relative to the closed state. But since we identified it, we calculated them relative to both states, just to make sure that we're actually getting the final state. So it's an absolute binding free energy, so it has to be relative to the final state of the protein and not a metastable state like this one. This one, you can look at the experiment. The correlation is not perfect because I use bootstrapping, so it includes the experimental error as well. So it's not too far from what you see from other absolute binding free energies, so the root mean square error around 1 for the closed state. And the correlation coefficient is not too bad, 0.7 for TIP3 and 0.83 for SPCE, both with GAF parameters. So one of the referees said, what if you try this for different binding poses? Can you tell which one is the correct binding pose doing this? And we actually did it, and it was successful for these 2 ligands to actually here. This was done using dock 6.7, so this was ranked second in the docking, but calculating the binding free energy, we got the correct pose. You can actually see from the RMSD here. So it did work. And this one, this RFX208 is very similar to this ligand, but they bind in completely different ways. So can you tell that similar ligand bind in a different way using binding free energies calculation? And we could tell it. Actually, if you the one that was modeling this very similar ligand has a lower binding free energy, this pose here, compared to the two poses from the crystal structure A and B. So the idea was, can we automate this thing? Can we make this whole thing automatic? No human interference at all. Just throw it in like black box calculation. So I started writing this program. So this was done in simple scripting. So the idea that it's highly efficient, I have built a few of these machines, so I know. So the idea is you can build very cheap. Resources are limited in Brazil, so we don't have access to large supercomputers. So it's interesting, at least for me, to just build computers. You know, this is all different parts. So I bought this GTX 1070, and they have very nice performance of 200 nanoseconds a day with a system around 40,000 atoms using hydrogen mass repartitioning. So this is encouraging because if you want to build like homemade systems, you can get cheap, $1,800. You can get 400 nanoseconds a day, which is a cost around $4.5 per nanosecond per day. And this is not hard to build. I actually learned how to build this myself, just looking at PC Part Picker website, and they all work. They are very stable, and they have no crashes at all. So it's very, a very efficient way of low-cost absolute binding free energy calculation. So this is the program based on this paper, but it has a lot of new stuff. So the idea is to create this Python tool for black box absolute binding free energy calculations. And this is actually black box. You don't do anything. It does everything for you, and it just puts out the result with all the calculations and generation of parameters, everything. So we can use the docking refinement tool to see if you can actually perform better than machine learning tools such as most docking programs. And also ligand ranking too, but right now I'm more concerned about the docking refinement part. And also if you can adapt that to, you probably can adapt that to other systems. They are suitable to these umbrella sampling calculations. Mostly you can use the dummy atoms, the protein is not too large and it's not going to move around too much. And also that the ligand exposed to the solvent, so you can just pull it out. So what are the input that you need? So once you choose a new protein, all you have to do is choose 3 anchors for the protein, the same way as the bromodomain. And you also need a reference PDB file. So you can align that manually on VMD or Chimera if you want. Choose the anchors, and from that, all the ligands are calculated automatically. All the binding free energies for different ligands and different poses are calculated automatically. You can also choose different things. You can restrain, apply conformational restraints that you're going to remove, attach and remove, calculate the free energy of that for a given protein backbone range, which is optional. You can choose the water model that you want, SPCE, tip 3P or tip 4P. Number of steps for the various stages. Force constants for each restraint. Number of ions if you want to perform neutralization, if you just want to neutralize the system. Temperature, and also the positions and weights for the different APR windows. The positions for the pulling, and then the weights for the attaching and releasing. So all of these have default values, but these two you have to, once you start with a new protein, you have to define them. So this is the workflow of the program. So once you run it, you need 2 sets of, you can run it using 2 things. Either you get a folder with all of your dock poses and your receptor structure, or you start from the crystal structure. If you start from this, it creates the PDB complexes automatically for you. And the crystal structure you don't need because the ligand is already there. So it's the co-crystal structure. So first it's going to obtain the ligand bonded and non-bonded parameters using GAF and also AM1 BCC. Then you're going to align the system and then choose the ligand anchors, which is automatic now. And then also place the dummy atoms, which is also done in the workflow. So the only part, once you start here, you don't do anything. Only thing you do is compare the poses afterwards. So then you're going to solvate the system with the chosen number of water molecules, generate the restraints based on the initial state, and from that you're going to do equilibrium simulations. Why? Because sometimes you can, I see the phase space, of the system like full of little holes. So hopefully I can get a state from the from the docking close. So the equilibrium is, maybe it falls into a little hole, and then the API is to see how deep that hole is. So which one is the lowest energy state. So after that, after we solvate the system, we perform equilibrium simulations. Just start with the ligand with the translation and rotational restraints apply, and then you slowly release them. So you leave a chance for the protein to adapt to it, or else it might just unbind very quickly. So then you check if the ligand is still bound. If it is still bound, I just consider that this pose is unstable, and I just throw it out. If it remains bound, then I do everything again. I realign the system, not too much because the system is still well restrained, the protein, but then I redefine all the anchors. Why do I have to redefine all the anchors? Because sometimes the ligand moves, so I have to choose the anchors again. Then reposition the dummy atoms, redefine the restraints. Then I pull it out from the binding site to book, generate all the APR windows, calculate all the binding free energies using the multi-state band acceptance ratio, and then finally I compare all the poles. So this is the workflow of the program. So just run it, and then it does everything here is done inside the program. So the system preparation, it starts with doing the protonation of the ligand. I have more success using Babel than the reduce from Amber, so I use Babel for it to protonate it. Then I use the AM1 BCC charges, which are quick. You just run like a simple MOPAC QM, and then you use the feeding from this paper here. And then you use the GAF parameters for the bonded ones, and also the LJ parameters, the atom types. So you align the system. So the system is not going to be aligned, not the receptor from the docked poles, and also the crystal structure is not going to be aligned. So you do have to align it because you have to pull it along the Z coordinate. So I use this very nice program called Mustang from the University of Monash, close to where I did my PhD in Sydney. So you just align this, because the good thing about it is just first it does a sequence alignment, and then it does a geometric alignment. So I can use the same reference structure for all bromodomains because it's going to align the system and then put it together. So using this, it's inside the program workflow. Then I get a system already aligned for me to pull it out. Then I plus the dummy atom. So here I have to be careful choosing the ligand anchors, because I cannot. There's something called a gimbal lock, or if you can call it a singularity on Euler angles. So well, this is later on. So first I choose the first ligand anchor. So I choose this, I call like a strike zone. So it's just a little square here that is placed based on the first protein anchor, where I choose the first ligand. So it's probably a part that's deep in the binding pocket. So I make sure that the first ligand anchor is the one closest to the protein. Then I choose the second ligand anchor with a minimum distance, and also the closest angle that I can to 90 degrees. Why is that? Because I don't want an angle that's too close to 180 or 0, and I don't want the distance to be too small. Then because I'm going to have to apply, so when we apply this angle in the dihedral restraints, these are all torsion springs. So it's actually, if you have the R sine of theta here, which is very small, you have to apply a very large force, and that's going to create instability in the system. So I choose the ligand anchors in an optimal way, using kind of a heuristic approach, but it does work, and it has a 100% success rate. It always is able to choose the ligand anchors and perform the simulation without any crashes. Because if you, like I say, if this gimbal lock, if this axis here aligns with this one, I have a gimbal lock or something close to a gimbal lock, and then I'm going to have trouble, because the forces are going to have to be too strong in order to turn this, to apply this torsion spring. So I don't want that. So that is why I have to have a kind of a special procedure to choose this. Then I place all the other 3 dummy atoms, the way I said before. These 5 atoms are all in the same plane, and these angles here are all 90 degrees. So as square as I can, both with the dihedrals and the angles. So the second and the third, using the same approach, just keep them far enough and close to 90 degrees. So this is the first part of the system preparation, just choosing the dummy and the anchor atoms. So I also apply conformational restraints in the ligand. So how do I figure out how to do this using single atoms? Well, you can go to the APRprotein file, and you can see all the dihedral without hydrogen. So I just choose every single dihedral and throw out the redundant ones. So I choose every single unique dihedral of the ligand, and I restrain it. And then I don't worry about angles and bonds, because they're already rigid by themselves, and not even impropers. So you can see the red ones here, these are all redundant. See 021, 021, 021. This is all the same torsion. So I just choose one of them. Same thing with the orange here, 21, 24, 24, 21. You have to know that this is actually, to get the atom index, you have to make this calculation here. So any impropers, I don't worry about them, because just to use the usually sp2 groups, keep them planar. So this works very well. The ligand is quite rigid, and I have to do that because since I have to choose automatically the ligand anchors, I have to make sure the ligand is rigid. So then I apply this protein backbone restraint. So what do? I just choose this backbone range. Okay, I want to restrain. This is the ZA loop, so this is very flexible. I don't want this stuff moving around when I pull the ligand out. So I just restrain this part, choose a sequence, let's say from residue 10 to 40, and I restrain all the phi and psi dihedrals. I don't worry about the omega ones because these ones are usually very rigid at 180. Rarely they're 0, but they're usually 180, so I don't have to worry about them. So this is all aromatic as well. So if I restrain these, I'm pretty sure that I make sure that this is going to be rigid during the absolute binding free energy calculations. So this is done automatically, and these I just have to choose the range when I define the file. So these ones are the conformational restraints. So the idea is just to shrink the conformational space because one of the biggest enemies of absolute binding free energy is just everything moving around. So if I can just attach and release restraint in the endpoint, and when I pull it out and do the calculations, everything is very, very tight, I get better convergence. So the equilibrium stage, you start from the dock pose, you slowly release the TR restraints like I mentioned before, 20 nanoseconds releasing the restraints, followed by 60 nanoseconds for the ligand to relax in the binding site. The pooling stage, I do just a series of simulations. I just do a series of simulations with 0.1 angstrom increments. You can also now use the NFE model from Amber, but there's some loss in performance, so I kept this one. But I can, if I want to calculate Jarzynski's equality, I can use the other one. But for now, I'm using this one. Just perform a series of simulations using small increments. And all the restraints in the ligand and the protein are included in this step here. So this is the ligand after the docking. After equilibration, it moves a little bit, and then I pull it out. So the APR windows, they're all obtained from the pooling stage, and the binding free energy has all these terms here. So I mentioned before, this is the protein conformational, then you apply the conformation restraints on the ligand, TR restraints in the ligand, pull it out, and then release them. This one is calculated analytically, besides this one, which is calculated just solving and Gaussian integral. All of the other ones are calculated using M-bar. So these are just showing again the setup of the system. These are all the restraints that I use for the calculations that I'm going to show here. This is the expression to release the ligand positional restraints. I solve this numerically using the trapezoid rule and the NumPy from Python. If you like solving integrals, you're probably going to say, yo, but this one varies much more than the Jacobian, so I can just put the average value in the Jacobian and put it out of the integral. Yes, you can do that, and the value is going to be very close. So you don't have to solve this numerically, but I do. You can have a very good approximation, just like I said, putting the Jacobian out of the integral and just solving these Gaussian integrals. Everybody knows square root of p over a. So this is how you relate these angles here with these ones. So like I said, this is just spherical coordinates, and this is not spherical coordinates because there's no r, but there's an extra 2 pi here, which is the ligand just turning around its own axis. So 4 pi, which is the sphere, and then times 2 pi, which is the ligand, the other axis just rotating around itself. So this is the docking is performed. This is not manual either. The docking is performed based on the Calpaid workflow. So what this is, it just takes beforehand, before they release the PDB structure, it gets already the receptor structure. It already has the coordinates for the docking. And then I just modified the Python scripts from this workflow to output not just the first pulse, output all of them. So, and then I connected this to my workflow. So an output looks like this. So attach the protein conformation, attach ligand conformational, attach ligand translational, pull the ligand out, release the ligand translational, and then these ones here in a separate box. For the average, I use all samples, and for the error, I use just the subsampling, just because I noticed that the results are a little bit more robust if I use all samples for this one, and then just use the subsampling for the M-bar error. I have to, because it's a covariant matrix. So a total of around 1.6 for the APR, plus 80, plus 68 nanoseconds for the pooling and equilibrium. A total around 8.6 microseconds for a given ligand, or a total of 187 hours. So this is not very efficient, you can argue, but all this can be done using trivial parallelization. So you have a bunch of GPUs, it just takes a couple of hours, 2 or 3 hours for each calculation, if you have a bunch of GPUs available. So this is another advantage. You can do all of this just using trivial parallelization. So no loss of performance by parallelization, just because you can do everything independently using one GPU for each. They don't have to be connected or anything, or embarrassingly parallel. So if you use multiple GPUs, it becomes much quicker. So a few of the results that I started with the BRD4 one Bromodomain. So this one was successful. Actually, autodoc vena was able to get the correct pulse, but it moved during equilibration. This one was very similar, and then it found the correct one during equilibration, and it was the lowest, or the lowest binding free energy here. So in this case, and it was also, the crystal structure also moved. So this is not supposed to happen, but it does sometimes. And what moves is just this ring here. It was just, this dihedral here was just getting out of place. Why? Because it's not just the ligand, you also have the protein around it. So maybe you can argue here that the protein adapted better for this, and here the protein found a different state that made the other one for the ligand more favorable. Not when I pull the ligand out, but overall. So you can see here the top 3 poses. Here had the lowest binding free energy, so it was successful, but it's not 100%. Here is not what happened. Actually, for the 2 top poses from autodoc vena, the binding free energy was actually lower than the binding free energy for the crystal structure. So this was not supposed to happen, but it did. But the correlation between, you see that the ranking is very similar between the binding free energy calculations and the autodoc, which I think is interesting in itself. Completely different methods. One is purely physics-based method, and another one is a machine learning method. And to see a very good correlation here, it's very interesting. This, even though the RMST here is high, the insertion is the same. So these ones, they're all inserted in the binding site correctly, all 4 of them. This is the insertion part in the binding pocket. So they're inserting the binding pocket correctly, but this part here and this one was this dihedral here, they were incorrectly placed. Here, similar, I got this one, second one, and this one was more successful. See, in the equilibration, I found the correct poses here, and for this one, I got one that was higher in the crystal structure, and this one was much better. So the crystal structure was usually higher, and it agreed very well with the other ones. And this one as well. This one, it could not, so here, the top one was not the top one from the autodoc, but it found the lowest binding free energy for this one, and also agrees well with the crystal structure. And finally here, here this one is similar, but this one is flipped, because I'm in a hurry now, sorry. And then this, autodoc was not able to find the correct crystal structure, but here it did find the lowest binding free energy when the crystal structure was done. And here, both autodoc vena, also robust calculations here, autodoc vena, the first one and also this one, very similar binding free energies, and it was also the correct one.
We're going to have to go to your conclusion slide.
Yeah, that's
all right.
Okay. So now it can perform slightly better than autodoc vena. Problems encountered might include lack of equilibration and sampling, steric effects, convergent issues, and also irreversible work being performed, which you don't want that. Now, right now, I'm just tuning the parameters, add conformational change to the workflow, add alchemical calculation, apply relative restraints, test no equilibrium methods, and include. So basically, just keep adding stuff all automated, so we can all do all of this without any manual interference. I would like to thank Mike Wilson and Hugh Herxia from UCSD, which are supporting me in this work, and thank you very much.
One question for Germano.
Sure, Chris, great work. It's nice to see this procedure automated. Question is, would including a protein conformational change break the embarrassing parallelism that you have? Because presumably you'd need to see the conformational change start to happen at each window in order to have decent phase-space overlap for protein conformation between the different windows.
You mean if the conformational change is too large?
Yeah, yeah. And in order to have if you want to have the protein conformational change, you need to have overlap the protein conformation between the windows, and so.
Yep.
You know, I don't know if that will support the kind of embarrassing.
No, the idea is not really to get the conformational change of the protein. It's just to keep a part rigid, because when I do the pulling, I don't want the protein to deform. So it's more like in the bind. So as long as it doesn't change too much in the binding site and in bulk, it's okay. But you're right. If there's a large conformational change, especially if it's irreversible, I'm going to have overlap problem. So I have to look at it in the apo state and look at it in the bound state, and then just make sure that I'm actually just making it more rigid. I'm not actually changing it too much. Yeah. So there has to be overlap, and I check that. So if not, I have to use that actually getting the APR to actually get the conformational done, and use umbrella sampling for that as well.
All right, a couple of quick announcements. There are two discussions.